Somewhere in a physics journal, the solution to interstellar travel already exists. The math checks out. The propulsion is real. Engineers have run the numbers, argued about them, and arrived at the same conclusion. We know, in principle, exactly how to reach another star. The problem is not the science. The problem is where the science sends you. Because the only engine powerful enough to cross the galaxy is not something we built. It is something the universe built for us, 4 billion years before we existed, out of collapsed stars and stolen light and the wreckage of dead suns. Tonight, we are going to follow the physics wherever it leads, and I promise you, you are going to wish it led somewhere a little less terrifying. If you are new here, welcome. Stay until the end, because the solution to interstellar travel has been sitting in the physics textbooks for decades, and nobody told you the part that should have made headlines. The math works, the propulsion is real, the highway already exists, we just forgot to mention where it goes, and the deeper you follow the equations, the less comfortable the answer gets. Now, let us get into it. Part 1. We already know how to leave the solar system. Here is something that should unsettle you a little. The physics of interstellar travel is not a mystery. We're not sitting here waiting for some revolutionary breakthrough, some eureka moment that rewrites the textbooks. The equations already exist. The propulsion concepts are already on paper. Engineers have already run the numbers, checked them twice, argued about them at conferences, and arrived at the same uncomfortable conclusion. We know, in principle, exactly how to leave this solar system and reach another star. The problem is not the physics. The problem is everything else. And when you start to understand what everything else means, the solution starts looking less like a triumph and more like a sentence. Let's start with what actually works. Laser sail propulsion, the kind being explored by the Breakthrough Starshot initiative, is mathematically valid. You take an enormous sail made of ultra-thin reflective material, you point a laser array at it from the ground or from orbit, and you push. No fuel, no rocket, just photon pressure applied at scale. The math says you can reach a meaningful fraction of the speed of light if your laser is powerful enough. We're talking about something on the order of 100 gigawatts of focused light to push a gram-scale chip to about 20% the speed of light. That's roughly 60,000 kilometers per second. To put that in terms you can feel, the distance from Earth to the Moon is about 384,000 kilometers. At that speed, you'd cover it in a little over 6 seconds. That is not a metaphor. That is just the number. Then there is fusion propulsion. Project Daedalus, a serious study conducted by the British Interplanetary Society back in the 1970s, proposed a spacecraft powered by nuclear pulse fusion. The design was not science fiction. It was a genuine engineering exercise. The conclusion was that a fusion-driven craft could reach roughly 10% of the speed of light, about 30,000 kilometers per second, and could theoretically make the trip to Barnard's star about 5.9 light-years away in roughly 50 years. That's one human lifetime, one career. Your kid could be born the day the ship launches and still be alive when it arrives. That is not impossibly far. That is just incredibly far. And at the top of the theoretical energy ladder sits antimatter propulsion. When matter meets antimatter, they annihilate each other completely, converting 100% of their combined mass into energy. Compare that to fusion, which converts less than 1% of mass into energy, or chemical combustion, which converts a fraction so small it barely registers. Antimatter is the most energy-dense fuel physically possible under known physics. The problem is containment, production, and the fact that we currently produce antimatter in quantities measured in nanograms at particle accelerators that cost billions of dollars to build and operate. But the physics? The physics is fine. The physics says it would work beautifully. Here is the thing about all of these solutions, though. They all break. Not in theory, in practice, in the actual universe, where space is not the clean empty canvas it looks like from a diagram. The moment you start pushing a spacecraft to a significant fraction of the speed of light, the universe begins pushing back in ways that are not immediately obvious, and are immediately catastrophic. This is the part where the story changes tone. At 1/10 the speed of light, a grain of sand, something you would brush off your hand without thinking, carries roughly the same kinetic energy as a tactical nuclear weapon. A speck of iron the size of a period at the end of this sentence would punch through a spacecraft like it was made of paper. And space is not empty. Interstellar space contains dust. It contains gas. It contains particles of hydrogen just floating there, minding their own business. At low speeds, those particles are irrelevant. At 30,000 kilometers per second, they become ionizing radiation. At 60,000 kilometers per second, they become a constant bombardment of high-energy projectiles tearing apart every molecule in your shielding. Cosmic rays already present a serious radiation problem for astronauts on the International Space Station. Now imagine those same cosmic rays, streams of high-energy particles zipping across the galaxy, but blue-shifted. When you travel toward a source of radiation at high speed, the energy of that radiation increases from your perspective. At 20% the speed of light, the radiation environment around your ship becomes something that no known material can fully stop. You're not just flying through space at that point. You're flying into a particle accelerator that stretches in every direction, and you are the target. Navigation becomes its own nightmare. At relativistic speeds, even the smallest trajectory error becomes enormous over the distances involved. The nearest star system, Alpha Centauri, is about 4.2 light-years away. That's roughly 25 trillion miles. If your aim is off by a fraction of a degree at the start of the journey, you miss by millions of kilometers at the end. And course corrections at those speeds require fuel you cannot carry, burns you cannot afford, and precision you cannot achieve because lightspeed communication lag means your navigation data is always already out of date by the time it reaches you. So here is where we land at the end of the first part of this problem. We have solutions, real ones, multiple ones, and every single one of them breaks at the same point, in the same way, for the same reason. It is not the engine, it is not the fuel, it is the universe itself, which turns out to be an environment so hostile at high velocities that the very thing you need to do, go fast, is exactly what makes everything else impossible. Physics gives you the key. The universe salts the road. That tension between a solved equation and an unsolvable environment is what pushed theorists toward an entirely different kind of question. Instead of asking how to push harder, they started asking whether there was a way to borrow. And that question, that subtle shift from pushing to borrowing, is where this story gets genuinely strange. Because when you start looking for things in the universe that already contain the energy scales you need, you find them. You just really, really wish you hadn't. Part 2. Every solution breaks the same way. There is a thought experiment that physicists sometimes use to make this viscerally clear, and once you hear it, you cannot unhear it. Imagine you're travelling at 20% the speed of light. Not metaphorically, actually travelling, inside a spacecraft, watching the stars shift colour ahead of you as your velocity begins to compress the wavelengths of incoming light. Now imagine a single hydrogen atom sitting in interstellar space. Just one atom. Hydrogen, the simplest element, a single proton with a single electron. Virtually nothing. From a standstill, that atom has essentially no energy relative to you. But at 20% the speed of light, from your reference frame, that atom is moving toward you at 60,000 kilometers per second. The kinetic energy of that collision, from your perspective, is equivalent to being hit by a particle accelerator beam. An interstellar space contains about 1 hydrogen atom per cubic centimeter on average. You're not flying through a vacuum. You're flying through a very thin but very real ocean of particles, and at relativistic speeds, every single one of them is a weapon. This is the interstellar medium, and it is one of the most underappreciated killers in the physics of space travel. When people think about the dangers of deep space, they think about radiation from the sun, about micrometeorites in the asteroid belt, about the cold and the vacuum. Those are real problems, but they are localized, manageable problems. The interstellar medium is everywhere between the stars. It is unavoidable. It is ambient. And at the speeds required for interstellar travel, it transforms from a background whisper into a constant punishing assault on every surface of your spacecraft. The numbers make it worse when you actually look at them. At 1/10 the speed of light, a single grain of interstellar dust, we're talking about a particle maybe 1/10 of a millimeter across, carries kinetic energy equivalent to several kilograms of TNT. At 2/10 of the speed of light, you are crossing the regime where even the individual atoms of the interstellar medium carry enough energy to cause ionizing radiation damage on contact. Your shielding absorbs these impacts, but in absorbing them, it also generates secondary radiation. Stopping the particle does not make the energy disappear. It converts into other forms, X-rays, gamma rays, particle cascades, that penetrate deeper into the structure of your ship. You can build thicker shielding, but thicker shielding means more mass, and more mass means you need more energy to accelerate, and more energy means a larger, more powerful propulsion system, which needs more energy, and the spiral begins. The rocket equation is the formal name for this particular torture. It was derived by a Russian schoolteacher named Konstantin Tsiolkovsky in 1897, and it describes the relationship between a rocket's final velocity, its exhaust velocity, and the ratio of its wet mass, mass including fuel, to its dry mass, mass without fuel. The equation is elegant. The conclusions it produces are obscene. To reach 10% the speed of light using an onboard rocket, even with fusion propulsion, your spacecraft needs to be almost entirely fuel. We're talking about a fuel-to-payload ratio somewhere between 100 to 1 and 1000 to 1, depending on your assumptions. That means for every kilogram of actual spacecraft structure, crew, instruments, life support, you need somewhere between 100 and 1000 kilograms of fuel. For an antimatter rocket, those ratios improve dramatically. But you're now talking about producing and storing hundreds or thousands of kilograms of antimatter, which is a problem so far beyond our current capabilities that it essentially relabels itself as science fiction, even though the physics is real. And here is the connection that matters for where this story is going. Every single approach to onboard propulsion hits the same wall. The wall is not technological in the sense that we simply need better materials or more advanced manufacturing. The wall is fundamental. It is written into the physics. The rocket equation does not care how clever your engineers are. It cares about the ratio of stored energy to ship mass, and at the speeds required for meaningful interstellar travel, that ratio becomes impossible to satisfy with any energy source you can carry with you. Which means, and this is the turn, the energy source cannot be on the ship. This is not a new idea. The laser sail concept already embraces it. The laser stays at home. The ship just catches the energy. But laser sails have their own wall, diffraction. Even the most perfect laser beam spreads out over distance. The physics of light propagation means that a beam aimed from Earth at a target 4 light-years away will have spread to an enormous diameter by the time it gets there, making it essentially useless for propulsion at those ranges. You can push a gram-scale chip to high velocity in the inner solar system. You cannot maintain meaningful beam intensity across light-years. The energy source has to be not just off the ship, it has to be distributed across the journey itself. And nothing in the solar system is powerful enough, concentrated enough, or positioned correctly to supply that kind of energy continuously along an interstellar trajectory. So physicists started looking outward. Not at our solar system, not at nearby stars, at the universe itself, asking what structures already exist that operate at the energy scales interstellar travel actually requires. And the answer they kept arriving at was uncomfortable. Not because the physics is wrong, because the physics is right, and it points somewhere terrifying. The only natural objects in the universe that generate energy at the scales you would need, that convert mass to usable energy at efficiencies that make fusion look like a candle next to a bonfire, that have already been operating as continuous energy machines for billions of years without any engineering from anyone, those objects are black holes. Not black holes as metaphors, not black holes as abstract curiosities, black holes as literal functional engines sitting in the galaxy waiting to be used. The moment you start thinking about them that way, you realise the question stops being, how do we get enough energy for interstellar travel? And starts being, how do we get close enough to the energy source without dying? And that reframing, that shift in what the problem actually is, changes everything about what interstellar civilization might look like, including why, if anyone out there has already figured this out, the galaxy might look very different from what we expect. But let's not get there yet. First, we need to talk about what a black hole actually is as an energy machine, because once you see it that way, you cannot unsee it. Part 3. Fusion is too small. Antimatter is too fragile. Stars are too slow. Let's do the energy math together, because this is where intuition completely fails, and you need the numbers in front of you to understand why the conclusion we're heading toward is not a fringe idea. It is, in fact, the logical endpoint of asking, what can actually power interstellar travel in a universe governed by the physics we know? Chemical energy, the kind that powers rockets today, converts about 1/10,000,000% of its mass into energy. The Saturn V rocket that took humans to the moon carried about 2 million kilograms of fuel and used the energy released by chemical combustion to push a payload of roughly 45,000 kilograms into orbit. Efficient by human standards, laughably inadequate by cosmic ones. If you wanted to push a crewed spacecraft to just 1% the speed of light using chemical propulsion, you would need a fuel mass roughly equivalent to the mass of Jupiter. That's not a practical limitation. That's physics laughing at you. Nuclear fission does better. A kilogram of uranium fuel fully fissioned releases roughly the same energy as about 20,000 tons of chemical explosive. But fission's efficiency, the fraction of mass actually converted to energy, is still less than 0.1%. Nuclear fission drove the development of civilization-scale power grids. It cannot drive a relativistic spacecraft. The numbers simply do not close. Fusion is the best candidate we have at human engineering scales. When hydrogen nuclei fuse into helium, about 0.7% of the mass involved is converted to energy. That sounds small, but compared to fission it represents a significant leap, and compared to chemical propulsion it is a fundamentally different category of power. The sun runs on fusion. It has been doing so for about 4.5 billion years and has enough fuel to continue for another 5 billion. Fusion-powered spacecraft concepts like Project Daedalus are real engineering proposals because the energy density is genuinely sufficient to reach nearby stars within timescales, measured in decades rather than millennia. But here is the problem with fusion for interstellar travel, and it is the problem that forces you toward the conclusion this story is building toward. 0.7% efficiency means that roughly 99.3% of your fuel mass does not become energy. It becomes exhaust, helium mostly. You're throwing away almost everything you started with. And because the rocket equation is brutally indifferent to how clever your engineering is, the mass ratios for fusion-powered interstellar travel remain punishing. The Daedalus study concluded that reaching Barnard's star in 50 years would require a spacecraft with an initial mass of about 50,000 tons, of which roughly 50,000 tons would be fuel. The payload, the actual science and structure of the ship, would be a few hundred tons sitting on top of a mountain of frozen fuel pellets. That is not a spacecraft. That is a fuel tank with a science lab stapled to the top. Antimatter is the theoretical ceiling of chemical energy conversion. Matter-antimatter annihilation is 100% efficient at converting mass to energy. Every single kilogram of antimatter you react with a kilogram of matter produces energy equivalent to about 86 million tons of TNT. If you had an antimatter rocket with a 100% efficient engine, the fuel ratios drop to something approaching reasonable. A crewed mission to Alpha Centauri might require only a few thousand tons of antimatter fuel rather than the absurd quantities fusion demands. The physics is genuinely compelling. The manufacturing problem is so severe it effectively removes antimatter from practical consideration for the foreseeable future. The world's most powerful particle accelerators currently produce antimatter in quantities measured in nanograms per year. A nanogram is 1/1000th of a gram. You would need something in the range of hundreds to thousands of kilograms for an interstellar mission. At current production rates, you would need to run every particle accelerator on Earth for longer than the current age of the universe to make enough fuel for a single interstellar flight. The physics permits it. The universe does not cooperate with the engineering. So here is where you end up after running through every energy source on the menu of human technology. Nothing works at scale. Not because we lack ingenuity, because the distances involved and the velocities required demand energy budgets that simply exceed what any portable power source can plausibly deliver. You need to borrow the energy from something that already has it, something that generates it continuously without being engineered, without being refueled, without decaying or running dry. And when you look at the universe asking that question, what already has the energy? The answer is not stars. Stars have the energy, but stars do not concentrate it in ways that are useful for propulsion. Stars spread their energy evenly in all directions across billions of kilometers of space. Stars are fire hydrants. You need a high-pressure nozzle. And that nozzle, it turns out, is the most extreme object physics permits to exist. But before we get to what you can do with it, we need to spend a moment understanding what a black hole actually does from an energy perspective. Because the number that comes out of that calculation is the number that changes the entire conversation about interstellar travel. Part 4. Black holes are not objects, they are engines. Most people think about black holes in terms of destruction. You get too close, you fall in, you're stretched into a stream of particles by tidal forces, a process physicists actually call spaghettification, which is both accurate and somehow funnier than it should be given what it describes, and you never come back. Gravity wins, nothing escapes, end of story. That framing is correct as far as it goes, but it is missing something fundamental about what black holes actually do, as physical systems, to the matter and energy around them. And once you see what they actually do, the destruction part starts to feel like a distraction from something far more interesting. A black hole in isolation, just a spherical mass with nothing around it, is actually pretty quiet. It sits there, it curves space-time, it does not radiate in any way classical physics can detect. If you placed one in the middle of an empty space with nothing nearby, it would be essentially invisible. No glow, no hum, no signal of any kind that conventional instruments could pick up. For something with a reputation as dramatic as a black hole's, that is a surprisingly underwhelming baseline. But black holes in the real universe are almost never in isolation. They are surrounded by gas, dust, the remnants of destroyed stars, the debris of galactic collisions, the constant inflow of matter drawn in by their gravitational fields over millions and billions of years. And when that matter falls toward a black hole, something extraordinary happens before it ever crosses the event horizon. The black hole wakes up, and when it does, it becomes something else entirely. As material spirals inward, it does not fall straight down. It orbits. Angular momentum, the same physical principle that keeps a spinning top upright and makes water spiral down a drain, forces the infalling material into a flattened disk of swirling gas called an accretion disk. This disk is not a gentle structure. The particles inside it are moving at significant fractions of the speed of light in the innermost regions, colliding with each other constantly, compressing against one another under the combined pressure of gravity and orbital dynamics. They generate friction. Friction generates heat. Enormous heat. The kind of heat that makes the surface of the sun feel like a mild afternoon. The inner regions of an accretion disk around a stellar mass black hole reach temperatures of millions of degrees Celsius, not thousands, millions. At those temperatures, matter does not just glow. It screams across the electromagnetic spectrum, pouring out X-rays and ultraviolet radiation and radio waves simultaneously, a broadband roar of energy that astronomers can detect from the other side of the observable universe. around a supermassive black hole, the kind lurking at the center of most galaxies, with masses ranging from millions to billions of times that of the Sun, the accretion disk can produce luminosities that outshine the entire galaxy it lives in. Every star in the galaxy, combined, outshone by a single disk of superheated gas spiraling into one object. These systems, supermassive black holes surrounded by actively feeding accretion disks, are called quasars. They are the brightest sustained objects in the known universe. Some quasars outshine 1 trillion stars, not 1 billion, 1 trillion, 10 to the 12th power. When you look at a quasar in a telescope, you're not looking at a star. You're looking at the light of 1 trillion stars produced by a disk of gas falling into a hole in space-time. That realization alone should give you pause, but we are just getting started. Now here is the efficiency number, and this is the number that changes the conversation entirely. A typical stellar nuclear fusion reaction, the process that powers the Sun, that has powered every star in the sky for billions of years, that represents the best sustained energy generation process nature produces at stellar scales, converts about 0.7% of its fuel mass into energy. That sounds small because it is small. The Sun is luminous not because fusion is efficient, but because the Sun is enormous and has been running for 4.5 billion years. Fusion is a slow burn at a terrible conversion rate, sustained by sheer quantity of fuel. An accretion disk around a black hole can convert somewhere between 6 and 42% of the mass of infalling material into energy before it crosses the event horizon. The specific number depends on whether the black hole is rotating. Non-rotating black holes, called Schwarzschild black holes, after the German physicist Karl Schwarzschild, who derived their mathematical description in 1916, just weeks after Einstein published General Relativity, while serving on the Eastern Front during World War I, which is a detail that somehow makes the achievement more remarkable, achieve about 6% mass-to-energy conversion efficiency. Rotating black holes, Kerr black holes, named for the physicist Roy Kerr, who derived their mathematical description in 1963, achieve up to 42% efficiency. 42%. Compare that to fusion's 0.7%, and you're looking at an energy machine that is roughly 60 times more efficient than the process that powers every star in the sky. 60 times. That is not a marginal improvement. That is not an incremental engineering gain. That is a categorical change in what energy conversion even means. Everything in the universe tends to rotate. Planets rotate. Stars rotate. Galaxies rotate. The clouds of gas and dust that collapse to form stars rotate, and that rotation is inherited by the objects they produce. Black holes formed from rotating stellar cores carry that rotation with them, compressed and concentrated into a mass so dense that the rotation does something the rotation of ordinary objects cannot do. It drags space-time. Not metaphorically, literally. A rotating black hole pulls the fabric of space-time around with it, the way a spinning ball bearing drags the surface of a viscous fluid. This effect is called frame dragging, and near a rotating black hole it becomes extreme enough to have a name of its own, the ergosphere. This is the region surrounding the rotating black hole where space-time is being dragged so severely that it is physically impossible to remain stationary relative to the outside universe, even if you had an infinitely powerful engine pointed in the opposite direction. You cannot stand still in the ergosphere. Space-time will not allow it. You're being carried whether you want to be or not. But here is the crucial detail, the one that separates the ergosphere from the event horizon in terms of what it means for physics and for our story. You can enter the ergosphere and exit it. It lies outside the point of no return. You have not yet crossed into the region from which nothing escapes. You're in a place that is doing something extraordinary to space-time around you, but you can still leave. And Roger Penrose, the British physicist who won the Nobel Prize in 2020 for his work on black holes, recognized in 1971 that this combination, extreme space-time distortion plus the ability to exit, creates something that should not be possible by any intuitive understanding of how energy works. He described a process by which a particle entering the ergosphere could split into two pieces. One piece falls into the black hole carrying negative energy, a concept that only makes sense in the warped space-time of the ergosphere, where energy states that would be forbidden everywhere else in the universe become physically accessible. The other piece exits the ergosphere carrying more energy than the original particle brought in. The black hole loses a tiny fraction of its rotational energy to pay the bill. The escaped particle gains kinetic energy from the transaction. The books balance. Conservation laws are satisfied, and yet something has just extracted usable energy from a black hole using nothing but geometry. The black hole is a battery. The ergosphere is the withdrawal mechanism, and Roger Penrose wrote the instruction manual. The Blandford-Znajek mechanism, developed in 1977 by Roger Blandford and Roman Znajek, extended this further into territory that is almost difficult to describe without reaching for words that sound exaggerated but are not. Magnetic fields threading through the accretion disk and the ergosphere can extract rotational energy from a spinning black hole and channel it into relativistic jets, narrow focused streams of superheated plasma and electromagnetic energy launched from the poles of the black hole at close to the speed of light. These jets do not dissipate quickly. They do not spread out and fade. They maintain coherence across distances that dwarf anything else in the universe. The jet emerging from the galaxy M87, the galaxy that hosted the first black hole ever directly imaged in 2019, that image of the glowing orange ring that briefly appeared on every screen on Earth, stretches for about 5,000 light-years. A single column of energy, launched by a gravitational engine, sustained across 5,000 light-years of intergalactic space. That is roughly 1/20th the diameter of the entire Milky Way, expressed as a jet, as a directed beam, pointed somewhere specific. That word, directed, is the one that matters for where this story is going. A black hole does not just destroy, it launches, it focuses. It takes the energy of infalling matter and converts it, with efficiency that makes stellar fusion look primitive, into the most powerful directed energy output the observable universe produces. And that raises a question that the physics will not let you ignore once you have seen the numbers. If a black hole can accelerate particles to relativistic velocities and launch them in a coherent beam across thousands of light-years, could something deliberately positioned near that beam, a spacecraft, a sail, a receiver built by something that understood the physics, use that output for propulsion? Could the most destructive objects in the universe also be the most useful ones? The answer, it turns out, is not only yes, but yes in a way that is more elegant and more unsettling than almost anything else in theoretical propulsion physics. But to understand the mechanism, we first need to talk about what happens to space-time itself near a black hole. Because near the event horizon, space does not just curve. It bends the rules of motion so completely that the very concept of navigation changes. Thrust becomes irrelevant. Geometry becomes everything. And that shift, from pushing to following the shape of space, is where the road to the stars actually begins. Part 5. Why black holes start looking like a network. General relativity tells us that gravity is not a force in the classical sense. Newton described gravity as a pull, an invisible hand reaching across space between masses, tugging them toward each other at a distance, instantaneously, with a strength that falls off with the square of the separation between them. That description works extraordinarily well for most practical purposes. It got us to the moon. It predicted the orbits of the planets to remarkable precision for centuries. But it is not what gravity actually is. Einstein spent a decade after his special relativity paper of 1905 working toward a deeper description, and what he arrived at in 1915 was something that required an entirely new way of thinking about space and time themselves. Gravity, in general relativity, is not a force at all. It is a curvature. Mass warps the fabric of space-time around it, and objects moving through that warped space-time follow paths called geodesics, the straightest lines possible in curved geometry. From the outside, It looks like gravity is pulling things toward the mass. From inside the geometry, nothing is being pulled anywhere. Objects are just following the natural contours of the space they exist in. The way a marble rolled across a stretched rubber sheet follows the depression created by a heavy ball sitting on it, not because something is pulling the marble, but because the surface itself curves toward the center. This distinction, force versus geometry, might sound like philosophical hair-splitting until you apply it to a black hole. Because near a black hole, the contours of space-time become so extreme, so sharply curved, so geometrically unlike anything that exists in the weak gravity environments where human intuition developed, that the concepts of direction and speed and even time stop behaving the way any prior experience would lead you to expect. Time runs slower near a massive object. This is gravitational time dilation, and it is not a metaphor. Clocks on the surface of the Earth run measurably slower than clocks in orbit. GPS satellites have to correct for this effect, or they would accumulate position errors of kilometers per day. Near a black hole, this time dilation becomes extreme. At the event horizon itself, from the perspective of a distant observer, time stops entirely. An object falling into a black hole appears to freeze at the horizon, its image red-shifting into invisibility over astronomical timescales, never quite crossing over. From the perspective of the falling object, time proceeds normally, right up until it does not. The geometry of space-time near a black hole is not just curved. It is curved in ways that dissolve the ordinary meaning of the words we use to describe motion. A rotating black hole, and essentially all real black holes rotate, because the stars that collapsed to form them were rotating, and collapsing conserves and concentrates that rotation, does something that a stationary mass does not. It drags space-time with it. Not metaphorically. The rotation of the black hole pulls the fabric of space-time around with it in a physical, measurable, experimentally confirmed way. This effect is called frame dragging, and while it exists around any rotating mass, the Earth's rotation produces a tiny, measurable frame dragging effect that was confirmed by the Gravity Probe B satellite experiment completed in 2011 near a rotating black hole. It becomes so severe that it stops being a subtle correction and starts being the dominant feature of the local geometry. An object near a rotating black hole is not just subject to a gravitational pull toward the center. It is being carried along by the rotation of space-time itself, swept around in the direction of the black hole's spin, regardless of what any onboard engine commands. You can point your thrusters in any direction you like. The geometry wins, every time. This is not a technology problem, it is a physics statement. The universe, in this region, has decided which way is which, and your opinion on the matter is not relevant. Inside the ergosphere, that outer boundary of the rotating black hole's most extreme space-time distortion, which lies outside the event horizon and is therefore technically escapable. This effect reaches the point where remaining stationary relative to the distant universe becomes physically impossible. You're moving whether you want to be or not. The rotation of space-time has made motion mandatory, and as we discussed when we talked about the Penrose process, this mandatory motion in a warped geometry is precisely what allows energy to be extracted from the black hole's rotation. The geometry that forces you to move is also the geometry that can be made to do work, which is a sentence that sounds abstract until you see what it implies for a beam of light passing nearby. At a certain distance from a black hole, the precise distance depending on the mass and spin of the hole, light itself follows closed circular orbits. This region is called the photon sphere. It sits at roughly 1.5 times the radius of the event horizon for a non-rotating black hole, closer for a rotating one depending on the direction of orbit relative to the spin. The photon sphere is the distance at which the curvature of space-time is so great that a beam of light aimed perfectly tangentially, perfectly sideways, not inward, not outward, but exactly parallel to the surface of a sphere centered on the black hole, will simply circle the black hole indefinitely, tracing out a closed loop, returning to its starting point over and over again, without ever escaping and without ever falling in. Or at least it will do this until something perturbs it. The photon sphere is not a stable equilibrium. A photon nudged even slightly inward begins a death spiral into the event horizon. A photon nudged slightly outward escapes to infinity. It is a knife edge, an unstable orbit balanced on the cusp between capture and freedom. But it exists. It is real. And it means that near a black hole, light does not travel in straight lines. It travels in curves, in circles, in loops that return to where they started. Take a moment with that, because it is genuinely strange. Light, the thing that defines straightness in the universe, the thing whose path through empty space is the very definition of a straight line in the geometry of special relativity, is being bent by gravity into a closed curve. The fastest thing that exists, the thing nothing can outrun, is going around in circles. The universe is doing something near the photon sphere that has no analogue in any environment accessible to ordinary human experience. There is no everyday reference frame from which this makes intuitive sense. You simply have to follow the mathematics and accept that space-time in this region has a shape that permits it. And here is where this connects directly to the propulsion problem we have been building toward. Because if light can be bent into curves near a black hole, then a beam of laser light fired from a spacecraft in the vicinity of a black hole is not going to travel in a straight line either. It is going to follow the curvature of space-time. It is going to arc. And with the right geometry, the right angle, the right distance, the right orientation relative to the black hole's position and motion, that arc can bring the beam back toward the spacecraft, back as a returning beam carrying information about every gravitational interaction it experienced along its curved path. And if the black hole was moving while the beam was traveling, if the black hole is part of a binary system, orbiting a companion, carrying its warped space-time geometry with it through space, then the beam that returns is not the same beam that left. It has picked up energy from the interaction with the moving gravitational field. It comes back boosted, more energetic than it departed, and a spacecraft that absorbs the boosted beam has gained momentum it did not have before, without expending any reaction mass, without burning any fuel, without violating a single conservation law. The black hole paid the bill, the geometry arranged the transaction, the spacecraft collected the change. This is the core physical mechanism of the halo drive, formalized by Columbia University physicist David Kipping in 2019. The name comes from the halo-shaped path the laser traces as it loops through the curved space-time near the black hole's photon sphere. The concept is not new physics. It does not require anything beyond what general relativity already predicts and observation has already confirmed. It is, in a sense, a gravity assist, the same family of technique that Voyager used to gain velocity from Jupiter's orbital motion, but executed with photons instead of spacecraft, and mediated by the curvature of space-time instead of a simple gravitational tug. And gravity assists, it turns out, do not stop scaling when you move from planets to black holes. They scale upward in ways that become genuinely difficult to hold in your head until you run the numbers. Because the energy available in a gravitational interaction scales with the mass of the object providing it, and a black hole in a binary system is not Jupiter. It is not the Sun. It is an object that may contain the compressed remnants of tens of solar masses, moving through space at hundreds of kilometers per second as it orbits its companion, carrying with it a gravitational field so warped that light cannot travel straight through it. The energy available for extraction in a single halo drive passed near such a system is not marginally better than a planetary flyby. It is not 10 times better or 100 times better. It is in a different category of magnitude entirely, and that difference in magnitude is precisely why interstellar travel, when you think about it through the lens of the halo drive, stops looking like a distance problem. It starts looking like a routing problem. It starts looking like a question not of how to cross the space between stars, but of where the black holes are, how they are moving, and whether a path can be plotted from one to the next that keeps the energy budget in the black. Which turns out to be a question with a deeply unsettling answer, because the universe, when you map it by its black hole positions rather than its star positions, does not look random. It looks structured. And structured, in this context, means something that should probably keep you thinking long after this ends. Part 6. Gravity assists. Go from planetary to relativistic. The Voyager probes are probably the most successful examples of gravitational engineering in human history, and it is worth sitting with that phrase for a moment, gravitational engineering, because it sounds grander than what actually happened, and what actually happened was already pretty grand. In 1977, NASA launched 2 spacecraft, Voyager 1 and Voyager 2, on trajectories that took advantage of a rare geometric alignment of the outer planets. Jupiter, Saturn, Uranus, and Neptune were positioned in a configuration that recurs roughly every 175 years. The mission planners recognized that this alignment created an opportunity to use each planet's gravity and orbital motion as a free propulsion source, threading a trajectory through the solar system that would gain velocity at each encounter without burning a drop of additional fuel. It was, in the most literal sense, using the solar system's own machinery to do the work. Each flyby added velocity. Jupiter gave Voyager 1 a boost of roughly 35,000 km per hour, on top of the speed it already had from the rocket that launched it. Saturn provided another boost. Without these gravity assists, reaching the outer solar system would have required either dramatically more fuel, dramatically more time, or both. With them, Voyager 1 is now the most distant human-made object in existence, currently travelling through interstellar space at about 61,000 km per hour, having left the solar system entirely. It did this not because we built a bigger rocket, but because someone did the geometry carefully enough to notice that the planets were briefly arranged in a way that could be borrowed from. The universe offered a shortcut. We took it. This is not a trick, and it is not cheating. It is a fundamental consequence of orbital mechanics, and understanding exactly why it works is important for where this story is going. When a spacecraft passes behind a planet, behind in the sense of trailing the planet in its direction of orbital travel around the Sun, the gravitational interaction between the spacecraft and the planet is not symmetric in time. As the spacecraft approaches, the planet's gravity pulls it forward and accelerates it. As it recedes, the planet's gravity pulls it backward and decelerates it. In a perfectly symmetric encounter with a stationary planet, these two effects cancel exactly. You arrive at a certain speed, you trace a curved path, you leave at the same speed. Net gain, 0. But the planet is not stationary. It is moving in its orbit around the Sun at tens of kilometers per second, and that motion breaks the symmetry. The spacecraft, during the interaction, essentially borrows from the planet's kinetic energy. The planet slows down by an amount so tiny that no instrument could ever measure it. The mass difference is simply too enormous, but the spacecraft speeds up by a real, measurable, mission-critical amount. Energy is conserved. Momentum is transferred. No fuel burned. The universe does not give you something for nothing. It gives you something in exchange for the planet's orbital momentum, which the planet has so much of that the transaction is invisible on its end. Now take that logic, hold it in your mind clearly, and apply it to a black hole. Not to the black hole's gravity in isolation, but to a black hole that is moving, orbiting something, carrying its warped space-time geometry through space at high velocity. A stellar mass black hole, the remnant left behind when a massive star exhausts its fuel and collapses in a supernova explosion, typically contains between 5 and several tens of times the mass of the Sun. The Sun itself has a mass of approximately 2 times 10 to the 30th kilograms, a number so large it has essentially no intuitive meaning, but what matters is the ratio. A black hole used as a gravitational slingshot offers not just more mass than Jupiter, which already gave Voyager a 35,000 km/h boost, but orders of magnitude more mass, combined with a gravitational field so concentrated that its effects operate at relativistic scales rather than Newtonian ones. The geometry near a black hole is not just a deeper version of the geometry near Jupiter. It is a qualitatively different regime, one where general relativity rather than Newtonian gravity governs the interaction, and where the energy available scales accordingly. But mass alone, as we established, is not the key. A stationary mass gives you a curved path and returns you to your original speed. The key is motion. A moving mass, a mass with kinetic energy that a passing spacecraft can borrow from, is the mechanism. And in the universe, things move. Stars orbit the galactic centre at speeds of hundreds of kilometres per second. The Sun itself orbits at about 220 kilometres per second, taking roughly 225 million years to complete one circuit of the Milky Way. Black holes, being the remnants of stars or in some cases the central masses of galaxies, also move. They orbit, they travel, they carry their warped space-time geometry with them through space at velocities that, in the right configurations, represent kinetic energy reservoirs of staggering scale. And the specific configuration that makes the halo drive concept not just theoretically interesting but potentially practical, the configuration that is not exotic or rare but exists naturally in the universe in enormous numbers, is two black holes in orbit around each other. Binary black hole systems are not rare curiosities. We know they exist in abundance because of what happens when they stop being binary systems and become single ones. When two black holes spiral toward each other and finally merge, they release a burst of gravitational waves, ripples propagating through space-time itself, compressing and stretching the distances between objects as they pass, powerful enough to be detected across billions of light-years of space. The Laser Interferometer, Gravitational Wave Observatory, LIGO, achieved the first direct detection of gravitational waves in September 2015. The signal lasted about 0.2 of a second. It was produced by the merger of two black holes, each roughly 30 times the mass of the Sun, located about 1.3 billion light-years from Earth. The energy released in those 0.2 of a second was greater than the total energy radiated by every star in the observable universe during that same 0.2 of a second. Read that again slowly. Every star in the observable universe in that same window of time, outpowered by two black holes colliding for less than 1/4 of a second. The universe already builds and detonates these energy events naturally, continuously, scattered across cosmic history like depth charges, going off in an ocean too large to map. They are already out there. They have been out there for billions of years. We just recently acquired the instruments sensitive enough to hear them. LIGO and its sister observatories have now detected dozens of these merger events, and each detection is, in a sense, a death certificate, evidence that a binary black hole system that existed somewhere in the universe has consumed itself. But for every system that has already merged, there are presumably many more that have not yet reached that point. Binary black hole systems in the long slow phase before merger, still orbiting each other, still separated by distances that may take millions or hundreds of millions of years to close, still carrying the full inventory of their orbital kinetic energy intact. Two massive, rapidly moving objects, each one a gravitational engine of the kind we have been describing, ergospheres, photon spheres, frame dragging, the whole apparatus, orbiting each other in a gravitational dance that will eventually end in a burst of energy detectable across 1 billion light-years. Before that ending, they are exactly the kind of moving massive objects that a gravitational slingshot requires, except at a scale that makes Jupiter look like a speed bump. If you could position a spacecraft in the vicinity of one member of such a binary system, not near the event horizon, not inside the ergosphere, but near the photon sphere, that unstable region where light circles the black hole in closed orbits, and fire a laser at precisely the right angle, the curvature of space-time near the photon sphere would redirect that laser beam along a curved path that loops around the black hole and returns it toward the spacecraft. While that photon was making its curved journey, the black hole moved. It is in a binary orbit. It is always moving. The gravitational field that redirected the laser beam was itself in motion during the interaction, and that motion imprints itself on the returning beam as an energy boost. The photon comes back carrying more energy than it left with. The spacecraft absorbs it. The spacecraft accelerates. No reaction mass expelled, no fuel consumed. The orbital kinetic energy of the black hole, accessed through the geometry of curved spacetime and mediated by a laser beam, has been converted into spacecraft velocity. This is not a new invention. It is not a technology that needs to be built from scratch. It is a recognition, a realization that the universe already constructed this propulsion system billions of years ago, distributed it across the galaxy in the form of binary black hole systems, and has been waiting for something clever enough to notice it and figure out how to use it. The figure that emerges from David Kipping's 2019 analysis is 20% of the speed of light, 60,000 kilometers per second, reachable, in principle, using this mechanism. The distance to Alpha Centauri, 4.2 light-years, covered in roughly 21 years. That is within a human lifetime. That is a journey a person could begin and a different person could complete, and the civilization that launched them could still be standing when the signal of arrival came back. The physics permits it. The infrastructure already exists. The only remaining question, and it is not a small question, is what it actually takes to get close enough to a binary black hole system to use it. And that question, when you answer it honestly, is the part of this story that stops feeling like good news. Part 7. The Halo Drive. Stealing motion from space-time. Here is the core concept, stated as plainly as possible, because it deserves to be stated plainly before we get into the details that make it complicated. You have a spacecraft. The spacecraft is equipped with a powerful laser, not a laser pointer, not a military targeting system, but a laser of the kind that a civilization capable of interstellar ambition might plausibly construct, something that can generate a sustained, coherent beam of photons with enough intensity to matter at the scales we are about to discuss. Ahead of the spacecraft is a rotating black hole, or better yet, a binary black hole system, where two black holes are in orbit around each other, slowly spiraling inward over millions of years, each one carrying its full complement of warped space-time geometry, ergosphere, photon sphere, frame dragging, the entire apparatus we have been building toward. The spacecraft fires its laser toward the black hole, aimed not at the event horizon, not into the point of no return, but at the region just outside it, near the photon sphere, that unstable gravitational knife edge where light travels in closed circular orbits. The laser beam does not travel in a straight line. It cannot near a rotating black hole because space-time near a rotating black hole is not a flat surface on which straight lines exist as meaningful paths. It is a curved geometry, a warped manifold in which the path light takes is determined not by the direction it was aimed in flat space, but by the curvature of the space-time it is moving through. Near the photon sphere, that curvature is severe enough to redirect the beam significantly. The photons follow the geodesics of the local geometry, the straightest paths available to them in a space that is not straight, and those paths curve. They arc around the black hole. They loop through the severely warped space-time near the photon sphere, bending progressively as they approach the region where orbital light paths close on themselves, tracing a trajectory that no flat space intuition would predict from the initial aim of the laser. And then, and this is the mechanism, the thing that makes the Halo Drive not just a curiosity but a potential propulsion system, the beam comes back. It returns toward the vicinity of the spacecraft. The geometry that bent the beam inward also, at the right distance and angle, redirects it outward again, back along a curved return path that brings it back toward where it originated. But it does not return in exactly the same state it left in. Because while the photons were making their curved journey around the black hole moved. The black hole is part of a binary system. It is in orbital motion around its companion, travelling at high velocity, carrying its warped space-time geometry with it through space. The gravitational field that redirected the laser beam was itself in motion during the entire interaction, and a photon bouncing off a moving gravitational mirror, which is precisely the physical analogy for what is happening here, does not return with the same energy it departed with. It returns boosted. The interaction with the moving gravitational field imprints additional energy onto the photon, the same way a ball bounced off a moving wall comes back faster than it left. The photon picks up energy from the black hole's orbital motion. When it returns to the spacecraft, it carries more momentum than when it left. The spacecraft absorbs it. The spacecraft accelerates. No fuel burned. No reaction mass expelled. No violation of any conservation law. The orbital kinetic energy of the black hole has been converted, through the intermediary of a laser beam and the mechanism of curved space-time acting, as a dynamic mirror into spacecraft velocity. The black hole slows down by an amount so vanishingly small that detecting it would require instruments of a sensitivity that does not exist. The spacecraft speeds up by an amount that, accumulated over many passes or a sustained interaction, is genuinely interstellar capable. This is the halo drive. The name comes from the halo-shaped path the laser traces as it loops through the gravitational curvature near the photon sphere and returns. It sounds like science fiction. The mechanism is pure general relativity, derived from equations that have been tested and confirmed to extraordinary precision by a century of observation and experiment. It is not a new principle. It is the Penrose process, the extraction of energy from the kinetic and rotational energy of a black hole applied to photons rather than particles, mediated by the photon sphere's gravitational lensing rather than particle splitting in the ergosphere, but governed by the same fundamental physical logic. A rotating, moving black hole is a system that contains extractable energy. The halo drive is a method of extracting it using light as the intermediary. The elegance of it, once you see it, is almost uncomfortable. Nature built the extraction mechanism into the geometry. You just need to aim correctly. David Kipping's analysis, published in 2019 in the journal Acta Astronautica, worked through the mathematics of what a halo drive could theoretically achieve. The conclusion was that a spacecraft operating near a binary black hole system could be accelerated to approximately 20% of the speed of light. That's 60,000 kilometers per second figure, using only the photons the spacecraft's onboard laser can generate and the gravitational infrastructure the binary system provides. No propellant tanks, no fuel mass ratio problem, no rocket equation exponential penalty. The spacecraft does not need to carry the energy for its journey. It needs a laser and access to a black hole. The energy comes from the universe's own stored kinetic inventory, from the orbital motion of objects that have been accumulating that motion since the galaxy formed. It is, in the most literal sense, borrowing from the universe's savings account. The distribution of black holes in the Milky Way makes this more than a thought experiment for a single lucky location. Our galaxy contains an estimated 100 million stellar mass black holes, remnants of massive stars that lived fast and died in supernova explosions across the galaxy's 12 billion year history, plus Sagittarius A star, the supermassive black hole at the galactic center, with a mass of about 4 million times that of the Sun, surrounded by a dense concentration of stellar mass black holes in the region immediately surrounding it. These objects are distributed throughout the galaxy. Not uniformly, black holes cluster along the spiral arms, where star formation is most active, and concentrate toward the galactic center, where stellar density has always been highest, but they are present in every region of the galaxy that has undergone significant stellar evolution. 100 million is a large number distributed across a large volume, but it is not so sparse that the average distance between black holes is prohibitive. In well-connected regions of the galaxy, black holes are separated by distances of dozens to a few hundred light-years. At 20% of light speed, those gaps are crossable in timescales measured in centuries rather than millennia. Black holes are not obstacles to interstellar travel. They are, if the halo drive concept holds up under deeper investigation, the waypoints of it, the fueling stations, the ports, the infrastructure of a galactic transit network that the universe constructed without being asked to. And now we arrive at the part of the halo drive concept that nobody wants to spend too long looking at directly, because it is the part where the elegance of the physics collides with the brutality of the environment. Getting close enough to a black hole to use the halo drive mechanism is not merely technically challenging in the way that building a better rocket engine is technically challenging. It requires placing a spacecraft, and potentially a crew, and certainly irreplaceable instruments and systems in an environment that is, by any honest assessment, catastrophically lethal by the standards of everything we have ever built or operated. The photon sphere of a stellar mass black hole sits at roughly 1.5 times the radius of the event horizon. For a black hole with 10 times the mass of the Sun, a fairly typical stellar remnant, the event horizon has a radius of approximately 30 kilometers. The photon sphere sits at about 45 kilometers from the center, which means it sits about 15 kilometers outside the event horizon, 15 kilometers from the point of no return. To put that in terms that have some physical reality, 15 kilometers is the distance you might drive to reach the next town. It is the length of a moderate highway commute. It is nothing. In the context of operating a spacecraft near a black hole, 15 kilometers of margin is not a safety buffer. It is a rounding error. You're not in the vicinity of something dangerous. You're parked immediately adjacent to the most dangerous boundary in physics, in an environment where the gravitational gradient between the front of your spacecraft and the back is measurable and structurally significant, where the radiation environment from any associated accretion disk is intense enough to destroy electronics and biological tissue simultaneously, and where the gravitational wave emission from the binary companion is physically distorting the geometry of the space your spacecraft occupies in real time. All of these conditions are not incidental hazards that a sufficiently clever engineering team might root around. They are intrinsic to the mechanism. The radiation comes from the accretion, which is the same process that makes the black hole an energetically rich environment. The tidal forces come from the proximity to the photon sphere, which is the same proximity required for the gravitational lensing that makes the drive work. The gravitational waves come from the binary orbital dynamics, which are the same dynamics supplying the kinetic energy the drive extracts. You cannot have the halo drive without the environment that makes the halo drive lethal. They are the same thing. The engine and the hazard are one object, viewed from two different perspectives, and that inseparability is what defines not just the engineering challenge of interstellar travel, but the character of any civilization that achieves it. Because achieving it means something very specific about what that civilization has learned to survive. Part 8. Why the speed number matters. 60,000 kilometers per second is not arbitrary. Let's pause on that number for a moment, because it keeps appearing throughout this story, and it is not a coincidence or a convenient approximation. 20% of the speed of light, 60,000 kilometers per second. To get a physical feel for what that means before we discuss what it does to the physics of travel, consider this. The distance from Earth to the Moon is about 384,000 kilometers. At 60,000 kilometers per second, you cover that distance in roughly 6.5 seconds. The distance from Earth to the Sun, 1 astronomical unit, the baseline measurement of the solar system, takes about 2.5 minutes at that speed. You would cross the entire diameter of the solar system, out to the orbit of Neptune, in roughly 4 hours. These numbers are not meant to make the speed feel comfortable. They are meant to make it feel real, because 60,000 kilometers per second is a speed at which the universe stops being the place your intuition was built to navigate, and starts being a place governed by rules that require a different set of tools entirely. This is not an engineering round number. It is the threshold at which the physics of motion transitions from the Newtonian regime, where time is universal, where simultaneity is absolute, where the equations Newton wrote in the 17th century describe reality with sufficient accuracy for essentially all practical purposes, into the genuinely relativistic regime, where Einstein's equations are not a refinement of Newton's but a replacement for them, where time is not universal, where the experience of a traveller and the experience of a stationary observer begin to diverge in ways that are not philosophical abstractions, but measurable physical realities with direct engineering consequences. At 20% of light speed, you're not at the extreme end of relativistic effects. You're at the beginning of the regime where ignoring them will kill you or your mission or both. Time dilation is the most famous relativistic effect, and it is worth being precise about what it actually does at the speeds we're discussing, because the popular version of it tends toward the dramatic in ways that obscure its more subtle, practical implications. At 1% of the speed of light, about 3,000 kilometers per second, already far beyond anything humans have achieved, time dilation is approximately 1 part in 20,000. Your clock, if you're moving at that speed, runs slower than a stationary clock by about 4.5 seconds per day. Measurable in a laboratory, irrelevant for a mission. At 10% of light speed, time dilation reaches about 0.5%. Over a journey of 50 years, the crew would age roughly 3 months less than people on Earth. Still small, but now entering the range where precision timekeeping and navigation systems need to account for it. At 20% of light speed, time dilation is approximately 2%. Over a 50-year journey, the crew ages about 1 year less than people back home. Not the dramatic decades of difference that science fiction tends to deploy, but real, measurable, accumulated over the length of an interstellar mission into a discrepancy that matters for synchronization, communication timing, and the basic bookkeeping of a long-duration voyage. But time dilation, at 20% light speed, is actually not the most pressing problem. The most pressing problem is what happens to the radiation environment. When you move toward a source of electromagnetic radiation, the frequency of that radiation increases from your perspective. This is the Doppler effect applied to light, called blue shift, and it is not merely a color change. Frequency and energy are directly proportional for photons. Higher frequency means higher energy. At 20% of light speed, photons arriving from directly ahead of you are boosted in energy by a factor that depends on the precise geometry, but in the most relevant directions the boost is significant, on the order of 20 to 50% depending on the angle of incidence. Now apply that to cosmic rays. Cosmic rays are already the single worst radiation hazard in deep space. They are high-energy particles, protons, atomic nuclei, electrons, travelling at close to the speed of light, generated by supernova explosions and other high-energy astrophysical events, streaming through the galaxy in all directions continuously. Astronauts on the International Space Station receive elevated radiation doses from cosmic rays even within Earth's magnetosphere. On a deep space mission beyond that protection, cosmic ray exposure is a serious long-term health concern. At 20% of light speed, cosmic rays arriving from ahead of you are blue shifted to energies 20 to 40% higher than they would be at rest. Your shielding was designed for the cosmic ray spectrum as it exists at low velocities. At 20% light speed, that spectrum has shifted. Particles that your shielding would have stopped are now arriving with enough additional energy to penetrate further. Particles that were already penetrating are now depositing more energy in the structures and bodies behind the shielding. The radiation environment your engineers designed for is not the radiation environment you're actually travelling through, and you cannot stop to redesign the shielding. Navigation at 20% light speed introduces a category of problem that has no analogue in any vehicle humans have ever operated. The fundamental issue is that information travels at the speed of light, and you are travelling at 20% of that speed, which means the universe you're observing is not the universe as it currently exists. It is the universe as it was when the light you're receiving left its source. For objects a light second away, roughly the distance from Earth to the Moon, used here as a unit, the discrepancy between apparent position and actual position is 1 light second of travel time, which at typical orbital velocities corresponds to a position error of a few kilometers. Manageable. For objects a light minute away, the error grows. For navigational features a light hour away, you're working with information that is an hour old, and anything that moved during that hour has moved from where your sensors show it to be. At interstellar distances, this problem does not just scale linearly. It compounds with the fact that your own velocity means your position relative to everything is changing rapidly, and any model of where things are must account for both the light travel delay and your own motion during that delay simultaneously. Your navigation system cannot work reactively. It cannot see something and respond. By the time you see it, you have already passed where it was when the light left. Navigation at these speeds is an exercise in predictive modelling, building a sufficiently accurate simulation of where everything will be, based on where everything was and how everything moves, and trusting that simulation rather than your sensors, because your sensors are always showing you the past. Trajectory errors, which at low speeds are minor inconveniences corrected with small thruster burns, become existential concerns at relativistic speeds over interstellar distances. The mathematics is unforgiving. An angular error of 1 arcsecond, 1/3600th of 1 degree, smaller than the resolution of the naked human eye, at the beginning of a 4 light-year journey, translates to a position error at the destination of roughly 600 billion kilometers. That is approximately 4 times the distance from the Sun to Neptune. You do not miss your target by a little. You miss it by the width of a solar system. A course correction at 20% light speed requires either a significant fuel burn, which demands fuel you may not have budgeted for, or a precisely planned gravity assist maneuver, which requires that the gravitational infrastructure for that maneuver be in the right place at the right time, which requires that you predicted its position correctly, far enough in advance to plan the correction, which requires the predictive navigation capability we just established is already operating at the edge of what is theoretically achievable. Every error compounds. Every correction requires resources. Every resource spent on correction is a resource not available for the rest of the mission. You must be right at the beginning. The journey does not forgive imprecision retroactively. The communication problem sits at the intersection of physics and psychology, and it may be the hardest one to truly internalize. At 20% of light speed, heading toward a star 4 light-years away, you reach the halfway point roughly 10 years into the journey. If something goes wrong at that point, a system failure, a medical emergency, a navigation anomaly that exceeds your onboard ability to resolve, and you transmit a distress signal at the speed of light back toward Earth, that signal takes roughly 2 years to arrive. Earth's response, transmitted immediately upon receipt, takes another 2 years to reach you. 4 years of round-trip communication delay at the halfway point of the journey when you're at maximum distance from any help. By the time Earth knows you have a problem and formulates a response, you have either solved it with what you had on board, or the mission is over. There is no cavalry. There is no rescue. There is no consultation with the engineers who built the system that is failing. You're not a vessel in contact with a harbour. You're an isolated system, complete in itself, moving at a speed no human has approached, through an environment that requires active management of every interacting physical variable simultaneously, with a communication infrastructure that delivers answers to questions you asked 4 years ago. The Halo drive solves the propulsion problem. It does not touch this one. And this one, the survival problem, the isolation problem, the problem of being genuinely, operationally, irrecoverably alone in a machine at the edge of what physics permits, is a different category of challenge than anything the history of human exploration has produced. Which means that the civilization capable of routine interstellar travel is not just a civilization with better engines. It is a civilization that has solved something much harder than engines. And what that civilization looks like, and whether anything in the galaxy has already become it, is the question that gives everything we have discussed its full weight. Part 9. The Hidden Requirement. Nobody wants to say out loud. Let's be honest about what the Halo drive actually demands of the civilization trying to use it, because when you lay it out clearly and completely, without softening the edges, it sounds less like an engineering specification, and more like a requirement list assembled by something that actively wants to kill you. Every condition necessary for the drive to function is simultaneously a condition capable of destroying the vehicle attempting to use it. This is not a coincidence. It is a consequence of where the energy comes from and what kind of environment produces it. And understanding that inseparability, really sitting with it rather than glossing past it, changes what interstellar travel means as a civilizational achievement. To use the halo drive effectively, a spacecraft needs to operate in the vicinity of the photon sphere of a black hole. We have established what the photon sphere is, the distance at which the curvature of space-time is so severe that light travels in closed circular orbits, the knife-edge boundary between capture and escape, located at roughly 1.5 times the radius of the event horizon. For a black hole with 10 times the mass of the Sun, a fairly representative stellar remnant, the event horizon sits at a radius of approximately 30 kilometers from the center. The photon sphere sits at roughly 45 kilometers. The gap between the photon sphere and the event horizon is 15 kilometers. To place that in terms that carry some weight, 15 kilometers is a short drive. It is the distance a reasonably fit person could walk in 3 hours. In the context of spacecraft operations near a black hole, it is essentially nothing. You're not operating in the general neighborhood of something dangerous. You're parked at the edge of a 15-kilometer buffer zone between your spacecraft and the boundary from which nothing in the universe has ever returned. At that proximity, the tidal forces become a primary structural concern. Tidal forces are the difference in gravitational acceleration between different parts of an object. The near side pulled more strongly toward the mass than the far side, creating a stretching effect along the radial direction and a compressing effect perpendicular to it. On Earth, tidal forces from the Moon are what cause the oceans to bulge. They are gentle enough that you never feel them as an individual human being. Near the photon sphere of a stellar mass black hole, they are not gentle. The gravitational gradient, the rate at which gravitational acceleration changes with distance from the center, at photon sphere proximity to a 10 solar mass black hole, is steep enough that different parts of a spacecraft of any reasonable physical size are experiencing meaningfully different gravitational acceleration simultaneously. The nose of the spacecraft is being pulled toward the black hole significantly more strongly than the tail. The spacecraft is being stretched along the radial axis and compressed laterally. Every structural component is under a continuous tidal load that no material we have ever engineered was designed to withstand in that combination, with everything else happening simultaneously. The physics, at this proximity, is actively trying to disassemble your spacecraft into its constituent parts, and then further into a stream of particles arcing toward the event horizon. This is not a marginal stress that clever materials science might address. It is the same fundamental force that produces spaghettification. You're operating at the near end of the regime where that process begins. Then there is the radiation environment, which deserves its own careful accounting because it operates through multiple simultaneous mechanisms at photon sphere distance from an actively accreting black hole. Actively accreting black holes, the ones surrounded by infalling material, the ones embedded in the energetic environments that make them useful as propulsion sources in the first place, are surrounded by accretion disks generating X-rays and gamma rays at intensities that scale with the accretion rate and the mass of the black hole. The inner regions of the accretion disk around a stellar mass black hole can produce luminosities equivalent to millions of times the total energy output of the Sun, concentrated not into the broad visible light spectrum that solar panels are designed to handle, but into hard radiation, high-energy photons that penetrate materials deeply, ionize molecules, break chemical bonds, damage crystal structures and electronics, and deposit lethal radiation doses in biological tissue in fractions of a second. An unshielded human being at photon sphere distance from an actively accreting stellar mass black hole would receive a fatal radiation dose in a time frame measured in milliseconds. The radiation does not care about your mission objectives. Shielding sufficient to survive this environment would need to be substantial. Dense, high atomic number materials, lead, tungsten, exotic composites, arrayed in thicknesses calculated to attenuate the relevant photon energies to survivable levels. The mass required for adequate shielding at these radiation intensities is not trivial. It is potentially enormous. And here is where the design problem becomes a feedback loop with no clean exit. Every kilogram of radiation shielding you add to the spacecraft is a kilogram that needs to be accelerated during the halo drive maneuver. The halo drive's energy efficiency, the rate at which it can transfer momentum from the black hole's orbital dynamics to the spacecraft, is not unlimited. It operates within the constraints of the laser power available and the geometry of the photon-sphere interaction. More mass means slower acceleration for a given energy transfer rate. Slower acceleration means more time spent in the radiation environment. More time in the radiation environment means more cumulative radiation dose, which means the shielding that was sufficient for a short exposure is no longer sufficient for a longer one, which means you need more shielding, which adds more mass, which slows the acceleration further. The engineering spiral does not converge easily. Every solution creates a new version of the problem it was solving. A binary black hole system, the optimal configuration for halo drive operations, because the orbital motion of the companion is the energy source being tapped, introduces an additional hazard that operates through a mechanism unlike anything in conventional spacecraft engineering. Binary black holes in close orbit emit gravitational waves continuously, and as they spiral closer to merger, the amplitude and frequency of those waves increase. Gravitational waves are not hazardous in the way that radiation is hazardous. They do not ionize atoms or deposit energy in materials in the conventional sense. They interact with matter by distorting the geometry of space-time itself, alternately compressing and stretching distances in perpendicular directions at the frequency of the orbital period. Far from the source, these distortions are extraordinarily small. The first gravitational wave detection by LIGO involved measuring a space-time distortion 1,000 times, smaller than the diameter of a proton, across a 4-kilometer detector baseline. But near the source, near a binary system in the late stages of in-spiral, the amplitudes are not small. Near a merging binary, the space-time distortions become large enough to cause measurable physical effects in extended structures. Your spacecraft is not just being subjected to radiation and tidal forces, it is being rhythmically compressed and stretched by ripples in space-time itself, at a frequency that increases as the binary spirals tighter, with amplitudes that grow as the merger approaches. The structural fatigue implications of sustained gravitational wave exposure at close range to a binary black hole system are not something any engineering tradition has previously had to consider. We do not have material specifications for this loading condition because no engineering context before this one has required them. The truly uncomfortable realization, the one that this section has been building toward, is that none of these hazards are separable from the function. They are not side effects that a clever enough design might root around. They are not problems that exist at the interface between the propulsion concept and reality. Problems that could be solved with better materials or more computing power, or a more thoughtful safety architecture. They are intrinsic. The radiation comes from the accretion disk. The accretion disk is what makes the black hole an energetically rich environment in the first place. Remove the accretion, and you reduce the radiation, but you also reduce the energy density that makes the system useful. The tidal forces come from the proximity to the photon sphere. The photon sphere is exactly where you need to be for the gravitational lensing that returns your laser beam with an energy boost. Move farther from the photon sphere and the tidal forces decrease, but the drive mechanism weakens because the lensing geometry becomes less favourable. The gravitational waves come from the binary orbital dynamics. The binary orbital dynamics are the source of the kinetic energy you are extracting. A binary system further from merger emits less gravitational wave power and poses less structural risk, but also has lower orbital velocities and provides less energy per interaction. In every case, reducing the hazard means reducing the function. The engine and the threat are not two different things. They are one thing, and your relationship to interstellar travel is defined by which side of that unity you're capable of inhabiting. What this means is that an interstellar civilization built on halo drive infrastructure is not a civilization that found a safe road between the stars. It is a civilization that determined there is no safe road, that the only road runs through environments that should by any reasonable standard be fatal, and then systematically solve the problem of surviving those environments well enough to use them. The on-ramp to the interstellar highway is inside the most energetically hostile region that nature produces. You cannot approach the highway from a safe distance. You cannot send a probe ahead to confirm the conditions are acceptable. The conditions are never acceptable by the standards of anything we have built. They are only acceptable by the standards of something that has spent an unknown amount of time and effort specifically engineering itself and its technology to function where nothing should function. That is a filter. A real one. A filter that any interstellar civilization, anywhere in the galaxy, using anything like this mechanism, must have passed through. And filters of that severity have implications for a question that has been sitting quietly underneath this entire conversation. The question of where everyone else is. The question of why the galaxy sounds so empty, when the physics suggests it probably should not be. But before we get there, we need to look at what the galaxy actually looks like when you stop mapping it by star positions and start mapping it by black hole positions. Because the structure you find when you do that is not random. And it was not built by anyone. It was just always there, waiting to be read correctly. Part 10. Interstellar travel stops being about distance. Here is a shift in perspective that seems obvious once you have it, but genuinely requires everything we have built together to land with the weight it deserves. So let's take it slowly, because the reframe is the point, and rushing past it would be a mistake. When you think about interstellar travel as a distance problem, which is the natural way to think about it, the way every popular account of space exploration frames it, the way it feels when you look up at the night sky and register that the stars are very far away, the galaxy presents itself as something close to impossible. The numbers are simply too large for comfort. The Milky Way is approximately 100,000 light-years across. A light-year is the distance light travels in 1 year, moving at 300,000 kilometers per second, which works out to roughly 9.5 trillion kilometers. 1 light-year. The galaxy is 100,000 of those. The nearest star system, Alpha Centauri, sits at 4.2 light-years, a distance so comparatively small that it is sometimes described as practically next door, which tells you something about how the human mind handles numbers at these scales, because 4.2 light-years is about 40 trillion kilometers, and there is nothing practically next door about it. At 20% of light speed, the speed we have been using as our reference point for halo drive performance, the trip to Alpha Centauri takes 21 years. One way. The galactic core, the region around Sagittarius A star where black hole density is highest, and the gravitational energy infrastructure is most concentrated, sits 26,000 light-years from Earth. At 20% light speed, that journey takes 130,000 years. The scale of the galaxy, even at the velocities the halo drive theoretically enables, seems to reassert the impossibility of the project every time you look at it directly. But here is the reframe. What if distance is the wrong variable? What if measuring the problem in light-years is like measuring the difficulty of sailing across an ocean by counting the water molecules you have to displace? Technically accurate, completely useless as a guide to what actually determines whether the crossing is possible. The ships that crossed the Atlantic did not succeed because the Atlantic got shorter. They succeeded because they found the winds and the currents, the energy infrastructure of the ocean surface, and routed their journeys through the places where that infrastructure was accessible. A ship that ignored the trade winds and sailed directly against the prevailing currents would take far longer, expend far more energy, and face far greater risk than one that accepted a longer route in exchange for travelling with the available energy rather than against it. The distance between ports was never the primary variable. Access to usable energy along the route was. Apply that logic to a galaxy populated with 100 million stellar mass black holes, and you get a picture that looks nothing like the map of empty distances. When you think about interstellar travel as an energy access problem, when you replace the question of how far with the question of how close are you to usable gravitational infrastructure, the entire structure of the problem reorganizes. The question stops being how do we generate enough energy to cross the space between stars and becomes where are the black holes? How are they moving? And can we plot a route from one to the next that keeps the energy budget in balance? Distance recedes as the primary variable. Topology, the structure of connections between accessible nodes, becomes the thing that matters. And the galaxy, mapped by black hole positions rather than star positions, does not look like a void. It looks like a network that was always there, waiting to be read. The distribution of stellar mass black holes in the Milky Way is not uniform, and the non-uniformity is not random. It follows a physical logic that reflects the history of star formation across the galaxy. Black holes are the remnants of massive stars roughly 8 or more times the mass of the Sun, that lived fast, burned bright, and ended in supernova explosions. Massive stars form preferentially in regions of dense molecular gas, along the spiral arms of the galaxy, where gas compression from the spiral density wave triggers star formation at elevated rates. They live for only a few million years before exploding, which means they do not travel far from where they formed before leaving their black hole remnants. The black holes inherit the spatial distribution of the massive star population, which means they cluster along the spiral arms and concentrate toward the galactic center, where the density of gas and stars has always been highest, and massive star formation has proceeded at the greatest rate throughout the galaxy's history. Roughly 10% of all stars massive enough to produce black holes are estimated to have already completed that life cycle, giving the Milky Way a current population on the order of 100 million stellar mass black holes. Distributed across the galaxy's disk, which is roughly 100,000 light-years across and a few thousand light-years thick, that population produces an average spacing between black holes that varies considerably by region. In the outer disk, spacing can be hundreds of light-years. Along the inner spiral arms it decreases. Near the galactic center, it decreases further still, to the point where black holes are separated by distances measured in light-years rather than hundreds of them. This variation in spacing is not just a statistical curiosity. It is the topology of the network. The regions where black holes are densely packed and binary systems are more common, where the probability of finding a halo drive capable configuration within achievable range is highest, are the highways. The sparse outer regions of the galaxy are the dead ends, the places where the network thins to the point of impracticality, where jumps between nodes require more energy than the nodes can supply, where the routing problem has no good solution. A civilization navigating by this network would not expand uniformly outward from its home system in a sphere of influence that grows at a constant rate. It would expand along the corridors where the infrastructure is dense, reach the sparse regions and stop, find the next connected corridor and continue, tracing a pattern that follows the galaxy's gravitational topology rather than geographic proximity. The map of such a civilization's territory would look strange by any distance-based expectation. Disconnected pockets of activity along spiral arms, dense occupation near the galactic center, vast empty regions not because nothing interesting is there, but because the routing infrastructure does not connect through them efficiently. Sagittarius A star, the 4 million solar mass black hole at the galactic center, deserves special consideration in this topology because its position and mass make it the most powerful single node in the network. A supermassive black hole of that mass, surrounded by the dense concentration of stellar mass black holes that inhabit the inner parsecs of the galaxy, represents an energy infrastructure hub of extraordinary capacity. The galactic center is also, by any conventional measure, an extraordinarily hostile environment, intense radiation fields, extreme stellar density, the gravitational influence of the central mass reshaping the orbits of everything within thousands of light-years. But in the framework we have been developing, hostility and utility are the same thing expressed from different perspectives. The galactic center is hostile because it is energetically extreme. It is energetically extreme because it contains the highest concentration of gravitational power in the galaxy. Those two facts are the same fact. A civilization that can survive the galactic center has access to the hub of the entire network, the junction through which the maximum number of routes pass, the node with the highest connectivity to every other part of the galaxy. The cost of access is surviving the most extreme environment the galaxy contains. The reward is the most connected address in the Milky Way. What emerges from mapping the galaxy this way, by gravitational infrastructure rather than stellar coordinates, is something that the word topology only partially captures. It is a structure of nodes and edges, of hubs and corridors and dead ends, of routes that follow no straight lines, because straight lines are irrelevant in a space governed by gravitational geometry. Efficient travel is not travel in the direction of the destination. It is travel through the sequence of nodes that keeps the energy budget viable, regardless of whether that sequence points directly toward where you're going. A nearby star with no black holes in its vicinity might be genuinely harder to reach than a star 10 times further away that sits along a well-connected corridor of binary systems. Distance is a secondary variable. Access is the primary one. And access is written in the positions and motions of black holes that have been accumulating in their current configuration for billions of years, since long before anything in the galaxy was looking for routes between the stars. This reframe has an implication that is worth stating carefully, because it connects to something much larger than propulsion engineering. If this network exists, and the physics suggests it does, in the sense that the black holes are real, and their distribution is real, and the halo drive mechanism is consistent with general relativity, then any civilization in the galaxy that developed sufficiently advanced technology would eventually discover it. Not because they were looking for it specifically, but because it is the answer that falls out of the physics when you ask the question seriously. And if they discovered it and used it, the signatures of that use might not look like radio transmissions or megastructures or any of the things we have been scanning the sky for. They might look like anomalous gravitational wave detection rates, merger events that do not match the statistical distribution predicted by natural and spiral dynamics, binary black hole systems with orbital parameters that suggest something has been extracting energy from them on a timescale inconsistent with natural gravitational wave emission alone. We are not yet looking for those signatures with any systematic intent. We have only just begun to be able to detect gravitational waves at all. But the possibility that the evidence of galactic-scale civilization is already in our data, unrecognized because we have been looking for the wrong kind of signal, is a thought that the physics of the halo drive places directly on the table. And once it is on the table, it is difficult to clear away. Part 11. Black holes. Become infrastructure nodes. Let's build the picture of what a black hole-enabled interstellar civilization would actually look like. Not as a fantasy projected onto the physics, but as a logical extrapolation of everything we have established. The energy mechanisms, the network topology, the hazard function inseparability, all of it carried forward into the question of what a civilization looks like when it has solved, or is in the process of solving, the problem of using this infrastructure. Because the infrastructure itself does not need to be built. That is the part worth sitting with before anything else. The universe already constructed it. The 100 million stellar mass black holes distributed across the Milky Way, the binary systems among them, the supermassive central mass, the galactic jets extending for thousands of light years from active galactic nuclei. None of this required engineering. It assembled itself from gravitational collapse and orbital dynamics and billions of years of stellar evolution. The question facing any civilization that understands the halo drive is not how to build the network. The question is whether they can survive long enough near the nodes to use it. A stellar mass black hole in a binary system, the configuration that represents the ideal halo drive energy source, because the orbital motion of the companion is the kinetic energy reservoir being tapped, is already doing the work without any assistance. Right now, somewhere in the Milky Way, binary black hole systems are orbiting each other, their gravitational fields carving curved space-time geometries that would redirect a laser beam back to a waiting spacecraft with an energy boost encoded in the interaction with the moving gravitational field. They have been doing this for millions or billions of years. They will continue doing it until the orbital energy bleeds away into gravitational waves and the two holes merge in a burst of energy detectable across the observable universe. During all of that time, the propulsion resource is simply there, available, operating continuously, offering anyone who can get close enough the ability to steal velocity from one of the most massive moving objects in the galaxy. Nature built a fueling station. It just did not label it as such. A spacecraft capable of operating near the photon sphere of such a binary system, and we have been honest about what that capability requires: the radiation shielding, the tidal force tolerance, the gravitational wave resilience, the navigational precision at relativistic speeds, could execute a halo drive maneuver and emerge with a significant velocity addition, without consuming propellant, without burning fuel, without paying any cost beyond the energy needed to generate the laser and maintain positioning during the interaction. Then it travels to the next node. Another binary black hole system, perhaps dozens or hundreds of light years away, another halo drive maneuver, another velocity boost, or, near the destination, a deceleration using the same mechanism run in reverse. The laser aimed to return with less energy than it left with. The spacecraft giving momentum back to the black hole's orbital dynamics, slowing down through the same gravitational mirror that accelerated it. Island hopping, node to node, fueled by the galaxy's own stored kinetic energy at each stop, carrying no propellant beyond the initial journey to the first node. The nodes of this network would not be evenly distributed, and the unevenness would shape the civilization using it as profoundly as geography has shaped every civilization on Earth. Some regions of the galaxy are rich in black holes, the inner spiral arms, the galactic bulge, the dense stellar populations near the core. In these regions, binary black hole systems are relatively common. The spacing between usable nodes is manageable, and multiple routing options exist between any 2 points. A spacecraft traveling through these regions has choices. It can optimize for speed, taking the route through the most energetically favorable binary configurations. It can optimize for safety, taking longer routes that avoid the most extreme radiation environments. It can divert around a node that is approaching merger, a binary system in the late stages of inspiral, where gravitational wave emission has become intense enough to pose additional structural risks, and route through an alternative. Options exist because the network is dense. In the outer disk of the galaxy, the picture changes. Stellar density decreases. Massive star formation has been less prolific. Black hole remnants are more widely spaced, sometimes by hundreds of light years between usable configurations. The routing problem in these regions is not just difficult, it may be effectively unsolvable at the energy budgets the halo drive provides. A gap of several hundred light-years between nodes, in a region where no intermediate black hole systems exist in suitable binary configurations, is a gap that no amount of clever routing can bridge if the propulsion technology depends on node proximity. The outer galaxy is not inaccessible in principle. It is inaccessible in the same way that a coastline without harbours is inaccessible to a sailing civilization, not because the water is impassable, but because the infrastructure that makes passage practical does not exist there. This asymmetry, rich inner network, sparse outer reaches, would shape the expansion of any civilization using the halo drive in ways that would look deeply strange from a distance-based perspective. Such a civilization would not spread outward uniformly from its home system in an expanding sphere of influence. It would follow the corridors of gravitational infrastructure, moving rapidly along the well-connected inner spiral arms, reaching the sparse regions and finding itself effectively stopped not by any external barrier, but by the absence of the energy nodes that make further movement possible. It would concentrate near the galactic centre, not because the centre is a pleasant neighbourhood, it emphatically is not, but because the centre is the highest connectivity node in the entire network. Every route that passes through the galactic core can connect to every other route that passes through it. In network theory, this is called a hub, and hubs are valuable enough that the difficulty and danger of reaching them is frequently worth paying. Binary black hole systems in this framework become the ports of the interstellar network. Not just waypoints, but infrastructure nodes, places where spacecraft can be accelerated or decelerated, where energy is available in quantities no other natural structure in the galaxy can match, where routes converge and diverge, where the logistics of interstellar travel are transacted. The analogy to terrestrial ports is not decorative. Ports in the age of sail were not just convenient stopping points. They were the entire basis of the economic and political geography of exploration. Civilizations that controlled access to good harbours controlled trade. Civilizations located far from navigable water were isolated not by distance, but by infrastructure absence. The equivalent dynamic in a halo drive civilization is control of, or proximity to, well-configured binary black hole systems. Geographic luck, in an interstellar context, means being born in a solar system near a well-connected node. It means having access to the gravitational highway without having to travel an unbridgeable gap to reach the on-ramp. Galactic jets, the relativistic particle beams launched from the poles of supermassive black holes in active galactic nuclei, extending for thousands to millions of light-years along the rotational axis of the central mass, represent a separate category of natural infrastructure that a sufficiently advanced civilization might think about very differently than we currently do. We observe them as astrophysical phenomena, spectacular and energetic and scientifically informative. From the perspective of a civilization that has already mastered halo drive operations near stellar mass black holes, a galactic jet is something else. It is a directed stream of particles moving at close to the speed of light, sustained continuously, extending across distances that dwarf any other structure in the galaxy. If a spacecraft could couple to such a jet, position itself within the energy stream in a way that transferred momentum to the vehicle without destroying it, the acceleration available would be, by any conventional measure, extraordinary. Not the incremental boosts of node-to-node halo drive operations, but sustained relativistic acceleration along a corridor that might extend for millions of light years. The survival question is severe. The particle densities and radiation intensities inside a galactic jet are not environments where any material we know of could maintain structural integrity. But the same was true of the photon sphere environment before we imagined engineering capable of surviving it. The jet represents an upper bound on what the natural infrastructure can provide, a ceiling so high that reaching it would require capabilities beyond anything the halo drive alone implies. The political and economic geography of an interstellar civilization built on this infrastructure would be determined by access in a way that mirrors terrestrial history so closely it is almost eerie. Civilizations positioned near high-density black hole clusters would have propulsion advantages that no amount of technological ingenuity could fully compensate for in a civilization positioned in a sparse region. The physics of the network would create structural inequalities between civilizations based on nothing more than the accident of where their home star formed relative to the galaxy's gravitational topology. This would not be a temporary advantage that technology could eventually overcome. It would be a permanent feature of the physical geography, as durable as the black holes themselves. And the expansion patterns of such civilizations would be irregular, corridor following, concentrated along the spiral arms and dense toward the center, essentially absent from the sparse outer reaches, which creates a specific and testable prediction about where we should look for evidence of such civilizations, and a specific and unsettling interpretation of why we might be where we are. We might be in a sparse region of the network. We might be off the main corridors, not along any route that a civilization navigating by gravitational infrastructure would naturally pass through. Not hidden, exactly. Just not on the way to anywhere the network goes. And if that is the case, the silence of the galaxy is not evidence that we are alone. It is evidence that the traffic is somewhere else, moving along routes we have not yet learned to see, through infrastructure we have only just begun to understand. Part 12. The uncomfortable conclusion. We started with a simple claim. Interstellar travel is already solved in principle, and the solution is frightening. Everything we have walked through since that opening statement has been the work of substantiating it. laying down the physics layer by layer, building the case from first principles rather than assertion, so that when we arrive at the conclusion it carries the weight of everything that came before it, rather than asking you to take anything on faith. We are at the conclusion now, and it is not speculative. It is the logical endpoint of taking the physics seriously, following it wherever it leads without flinching when it leads somewhere uncomfortable. The halo drive is a mechanism consistent with general relativity. That sentence is worth pausing on, because general relativity is not a tentative framework or a working hypothesis. It is the most precisely tested theory in the history of physics. Its predictions have been confirmed by over a century of increasingly sensitive experiments and observations. The bending of starlight around the Sun, confirmed in 1919. The precession of Mercury's orbit explained where Newton's gravity failed. Gravitational time dilation, confirmed to extraordinary precision by atomic clocks on aircraft and in orbit. Gravitational waves, predicted by Einstein in 1916 and directly detected by LIGO in 2015. Frame dragging, confirmed by Gravity Probe B in 2011. The shadow of a black hole event horizon, imaged by the Event Horizon Telescope in 2019. Every prediction general relativity has made that we have had the technology to test, it has passed. And the halo drive is a consequence of general relativity. It does not require any new physics. It does not require exotic matter with negative energy density, the kind needed for warp drives or traversable wormholes. It does not require any concept that has not been validated by observation and experiment. It requires a rotating black hole, a laser, and a spacecraft capable of surviving near the photon sphere long enough to execute the maneuver. The physics underneath it is the same physics that runs GPS satellites, that predicted the gravitational waves LIGO detected, that described the image of M87's black hole before we had the instruments to capture it. This is not fringe physics. This is the established framework of the universe, followed to a conclusion that most people have not yet thought through. The energy the halo drive extracts is real energy from real systems. The orbital kinetic energy of binary black holes is not a theoretical abstraction. It is a physical quantity that LIGO measures indirectly every time it detects a merger, the energy that was in the orbital motion before the merger shows up as gravitational wave energy after it. We know binary black holes contain enormous kinetic energy reserves because we have watched that energy leave as gravitational waves and calculated the magnitude. The halo drive is a proposal for accessing a fraction of that energy before the merger consumes it all, using the mechanism of gravitational lensing near the photon sphere to mediate the transfer. The velocity it can impart, up to 20% of the speed of light in David Kipping's 2019 analysis, is genuinely interstellar capable in a way that changes the character of the problem. Not trips measured in millennia, not generation ships where the crew that arrives shares no living memory with the crew that departed. Trips to nearby stars measured in decades, within a human lifetime, within the operational lifespan of a well-built spacecraft. Within the window where the civilization that launched the mission is still the civilization that receives its transmissions from the destination. 20% of light speed does not make interstellar travel easy. It makes it possible in a sense that actually matters. The routing infrastructure the halo drive requires already exists, and this fact deserves emphasis because it separates the halo drive from almost every other serious interstellar propulsion concept in a fundamental way. Laser sail concepts require building enormous precision laser arrays in space. Fusion drives require solving controlled nuclear fusion at engineering scale, and then solving the fuel-mass ratio problem. Antimatter drives require producing antimatter in quantities that current technology cannot approach within any realistic projection. Every other concept requires building something that does not currently exist, at scales and costs that are either unknown or prohibitive. The halo drive requires using something that already exists. 100 million stellar mass black holes distributed across the Milky Way. An unknown but certainly non-zero number of binary systems among them, in configurations amenable to halo drive operations. The supermassive black hole at the galactic center. the galactic jets extending from active nuclei. None of this needed to be constructed. The universe built it over 12 billion years of stellar evolution and gravitational dynamics. The network is there. It has been there since long before Earth formed. The routes through the galaxy that an interstellar civilization would travel are, in a meaningful sense, already written, determined by where the black holes are, how they are moving, which binary configurations are energetically favourable, how the nodes connect. The map of the interstellar highway exists. It is written in the positions and motions of the most destructive objects in the galaxy, and we are only now developing the physics literacy to read it. The survival problem is real, and saying so is not a reason to dismiss the concept, but a precise description of what the concept actually demands. Operating a spacecraft near the photon sphere of a black hole, inside the radiation environment produced by an active accretion disk, while managing structural stresses from tidal forces and space-time distortions from gravitational wave emission, this exceeds our current engineering capabilities by a margin that is not small. It is not a gap that better materials or more computing power will close in the next decade or the next century under current trajectories of development. It is a categorical engineering challenge, the kind that requires not incremental improvement of existing approaches, but fundamental reconceptualization of what spacecraft design means. The shielding problem, the tidal tolerance problem, the navigation precision problem, the communication isolation problem, these are not independent challenges that can be solved separately and then assembled into a complete solution. They are coupled. The solution to one affects the constraints on another. Solving them simultaneously, in an environment where there is no room for iterative debugging because the first failure is final, requires a depth of understanding of the relevant physics that we do not yet possess, and an engineering tradition that does not yet exist. This is a characterization of what interstellar travel actually requires, not a reason to stop thinking about it, a precise statement of the work that remains. The universe, it turns out, is not randomly hostile to interstellar travel. The hostility is structured. It is specifically concentrated at exactly the scales and velocities where interstellar movement becomes meaningful. The radiation environment becomes lethal at the speeds you need. The energy requirements exceed any portable source by the margins required for realistic mission parameters. The navigational precision demands exceed reactive response capabilities by the light speed lag that governs all information transfer. And the solution to all of these problems, the halo drive, the gravitational energy network, the mechanism that makes the physics actually work, places you, by physical necessity, in the most extreme environments the galaxy produces. This cannot be a coincidence in any meaningful sense. Whether you frame it as cosmological design or emergent consequence of physical law, the structure is there. The universe filters civilizations that want to cross it. Civilizations that cannot master, or choose not to engage with, extreme gravitational environments stay home. Civilizations that develop the engineering and the will to operate at photon sphere distances from black holes get access to the network. The filter is not arbitrary. It is specifically calibrated to the physics of what interstellar crossing requires. You do not get the highway without first demonstrating that you can survive the on-ramp. There is a philosophical symmetry running through all of this that is genuinely difficult to dismiss once you see it clearly. The same tidal forces that would pull an inadequately engineered spacecraft into its component atoms are the forces produced by the same gravitational field that curves the laser beam and makes the drive work. The same accretion disk radiation that would be instantly lethal to an unshielded crew is generated by the same infalling material that makes the black hole environment energetically rich. The same frame dragging that sweeps a spacecraft off its intended course, if the navigation is wrong, is the same frame dragging that enables the Penrose process and makes energy extraction possible. Every feature of the environment that kills you is the same feature that powers you. The hazard and the mechanism are not opponents in this physics. They are the same phenomenon described from two different positions, one inside adequate shielding and one outside it. Your civilization's relationship to interstellar space is determined entirely by which side of that boundary you can engineer yourself to inhabit. The road exists. The mathematics describes it without ambiguity. The universe built it from collapsed stars and orbital dynamics and billions of years of gravitational evolution. It runs through ergospheres and photon spheres and binary and spiral systems and the relativistic jets of galactic nuclei, and it was there long before anything in the galaxy was capable of recognizing it as a road. It will be there long after our civilization has either found a way to travel it or quietly decided the cost was too high. And if something else in the galaxy has already made that journey, if some civilization at some point in the last several billion years developed the engineering to skim event horizons at 60,000 kilometers per second, to steal velocity from orbiting black holes, to navigate the network that the universe pre-installed in the structure of the Milky Way, then the silence we hear when we listen to the sky becomes a different kind of silence than the one that suggests we are alone. It becomes the silence of traffic on a highway we cannot see, moving through corridors we have not yet learned to map, between destinations we do not know to look for. Either no one has figured it out yet and we are early, or the ones who figured it out left and do not come back to where the network does not go. Or the universe's answer to the question of interstellar civilization is that the civilizations capable of it are defined by their willingness to drive directly into the most destructive structures in existence, and the ones who are not willing or not yet ready remain where they are, looking up, listening carefully, and hearing nothing. The road is already out there, we just cannot reach it yet, and somewhere in the honest acknowledgement of that gap between what the physics permits and what we can currently survive lives the most important question our species has not yet fully learned to ask.